we already know that the equation which gives the potential at a particular point due to a charged particle is given by V is equal to KQ divided by R. Way we find potential V is that V is equal to KQ divided by R. So K is nothing but 1 by 4 pi epsilon naught. So what does equipotential surface actually means? It just means that the surface which has equal amount of potential. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about electrostatic potential and capacitance. And in today's class, we'll be learning about dipole and its potential. So let's dive right into it. Before anything, let us consider what we actually know about the dipole. We know that there are equal and opposite pairs of charges and it is separated by a distance of 2a, and the dipole moment is given by P, which is equal to 2aq. So these are our initial considerations which we know about the particular dipole. And we know that it is a pair of equal and opposite charges separated by a distance of 2a. So when we have a point, let's say at r distance away from the center, we can say that the distances will be a each. So let us consider a point which is r distance away from the center of the dipole. Always make sure you put down a unit vector sign. Now, what we want to find out here is that what will be the potential at this particular point. So we have to find out what is the potential at that particular point. For that, we need to know what is the distance from this particular point to here and this particular point to here. So let's say this is a positive charge. Let's say A is positive, B is negative, and O is the origin point where the center line starts from. Then we can say that this particular distance is R1, and let's say this particular distance is R2. Now we have to find out what R1 and R2 is, because we already know that the equation which gives the potential at a particular point due to a charged particle is given by V is equal to KQ divided by R. So we already know K is 1 by 4 pi epsilon naught. So we have to find out what R is. And R is the distance from that particular charged particle to the point where we are calculating the potential is experienced. And we already know that this particular distance is A, and we know that the center line is making an angle of theta. From this point onwards, it's purely mathematical, and we are going to find out what R1 and R2 actually is. For that, we are going to seek the help of mathematics. So we can say that to find out R1, we first need to make sure we know the Pythagorean theorem. For that, we also need the base, the altitude, and everything. So there is actually a trick to finding out what R1 is. So there is a mathematical property which says that if the angle is really small, the two lines are almost proportional to each other. And this particular case, the distance of the dipole is really small, and the length we are considering, that the point we are taking is really far away from that particular dipole. So even if I have drawn it like this, the actual scenario is that the dipole is only this big, this much longer, and the angle is this much, which means that we are only considering this small angle. So we can say that these two sides are proportional to each other, and we can simply use that to our advantage and make mathematical assumptions. To begin with, we are first going to draw a perpendicular line from the central line to the point B, so that it is something like this. Make sure it is a perpendicular line, which means that this particular angle is 90 degrees. Let's call that point as M. So triangle BOM is a right angle triangle. Triangle BOM M is a right angle triangle. So why did we make it into a right angle triangle? So that we can find the distance which is R1. We can say that this particular distance will be equal to R1, which is that the whole distance, let's name it as C. So OC will be R distance, then R will be the distance from O to C. And if we can find out what OM is, we can subtract that from R, and that will be the distance of R1. Even though the figure illustrates that R1 will be more, in the actual sense I have just showed you, the angle is really far away, so that if we subtract that particular distance, those two sides will be proportional or almost equal in this case. So we have to find out R1. For that, we have considered the right angle triangle, which is MOB. And we got that triangle by joining or drawing a perpendicular from the central line to the end of the dipole, one end of the dipole. First, we are going to consider the cos of that particular angle. That is, the angle which is made by the central line and the dipole, that is theta. So we can write as cos theta will be equal to adjacent side by hypotenuse. That is adjacent side divided by hypotenuse, which means that adjacent side just means that it is the side right by that. So here is the angle theta, right by that what is the adjacent side and what will be the hypotenuse. Always remember, the hypotenuse will be the side opposite to the 90-degree angle, which means that here it is the 90-degree angle and the hypotenuse is A. The side A is the hypotenuse. So we know what is the hypotenuse. It is A, and we know what is the adjacent side, which is MO. So we can write it that MO will be equal to cos theta. Or we can simplify that and we can just simply write that MO is equal to A cos theta. So this particular distance MO is nothing but R minus this particular distance will give you the R1. Why we actually found out MO was that we need to find out what R1 actually is. For finding out R1, I told you earlier, it is very easy. You have to find out what the distance MO is and subtract that from the original distance, that is R, and that will give you R1. So in order to find R1, we can subtract this distance from the original distance, which is R. So we can write this MO as, we can write it as R1 equals R minus A cos theta. Let me just summarize that and explain it to you real quickly. It's a bit mathematical. That is, we are going to find out the reason why we did all this is to find out what R1 actually was. So in order to find out R1, one mathematical probability was that we could find out what the distance OM or MO was and subtract that from the original distance R, and that will be equal to the distance R1. So we found out what the distance OM was using the Pythagorean theorem, and we found out that it was A cos theta. So we rearranged it and we found out it was A cos theta. If we subtract that from the original distance, that is R, we would get R1. So that is how we got R1 is equal to R minus A cos theta. Now just like this, we also need to find out what is the distance R2. In order to find that out, we are going to extend this angle, that is the line R, backwards. We are going to extrapolate that so that we get a line like this. And then again the same thing we are going to do. We are going to draw a normal like this so that these two angles are equal. Again, this will be theta. If the angle MOB is theta, then automatically the angle AO, let's say this is N, AON will also be theta because opposite angles are equal. Then the same theory we are going to apply. We are going to find out what cos theta is, and then we are going to write it in the form of R2 is equal to that particular thing. So in this case, the angle, that is the 90-degree angle, will be ANO. So we can write it as ANO will be 90 degrees, and we already know that angle AO is A distance because it is half of the length of the dipole, and then we can write it as, let's say this is 1, then we can write from triangle ANO, we can write it that cos theta will be equal to adjacent side by hypotenuse, which will be equal to adjacent side, which is nothing but NO or ON divided by hypotenuse, which is A. So A cos theta will be equal to ON, but we want to find out in terms of R2, that is the distance R2. So same way, if we add this distance, it will be equal to the distance R2. In order to find out the distance that is CA, that is R2, we can just extrapolate this line backwards, draw a normal, and then solve it. Then we can find out the distance ON, and if we add that to the distance R, we will get what is R2. So we can just write it as R2 will be equal to R plus A cos theta. Don't worry if it's a little confusing, I'll just explain it one more time. So first, let's note down these two equations. So we got what R1 is and R2 is. Based on these two, we are going to go forward. Now, why did we find out R1 and R2? So that we can find out what is the potential at a particular point away from the dipole. So we can say that the way we find potential V is that V is equal to KQ divided by R. So K is nothing but 1 by 4 pi epsilon naught. In this particular case, we are dealing with a dipole, so that we have two potentials, that is due to plus Q and due to minus Q. So in order of plus Q, we can say that it is equal to KQ divided by R. And then let's say R1, and for minus Q, it will be equal to V is equal to minus KQ divided by R. The minus sign just indicates that it is a negative potential because it is a negative charge, and positive sign says that it is a positive charge and positive potential. So these are the two equations we need to consider. So now you know why we actually find out R1 and R2, so that we can substitute that in this particular equation in order to find out what is the actual potential. So we can say that the total potential will be equal to V1 plus V2, just like adding scalars. So we can say V is equal to KQ divided by R1 plus KQ divided by R2. And we have to consider the negative sign. It is just indicating the direction, or just saying that for that particular charge, the potential is negative. Okay, so we can just simply write it as, we can bring out the KQ outside, and we can say that 1 by R1 minus 1 by R2 will be the total potential at that particular point. Now, what is 1 by R1 plus minus 1 by R2? So it is simply R plus A cos theta and R minus A cos theta. So we can write the total potential as V is equal to KQ will be outside. We can write that 1 by R plus A cos theta minus 1 by R minus A cos theta. Now, we are going to cross multiply this and simplify this equation. That is, R minus A cos theta will come to this side, R plus A cos theta will come to that side, and these two will multiply together. So we can write it as KQ into R minus A cos theta minus r plus a cos theta divided by r plus a cos theta into r minus a cos theta. So if you observe carefully, this is nothing but a plus b into a minus b. That is a, and a cos theta is b. So a plus b into a minus b. So a plus b into a minus b is nothing but a square minus b square. So we can write this as, we can write the denominator part as q into, let's say, r square minus a square cos square theta. And then the numerator part, we are going to multiply this negative sign inside. So minus r minus a cos theta. So minus r and plus r will cancel each other out, and we can write minus a cos theta plus minus a cos theta. So we can write minus 2a cos theta. And this will be the final equation. So kq into 2a cos theta by r square minus a square cos square theta. We are not just over here. So we are going to do is that we are going to multiply this kq inside, and don't worry about the negative sign. The negative sign is just indicating that the direction or the way, the nature of the dipole. We can just avoid that. We can write this as k 2aq, let the minus sign be here, 2aq into cos theta divided by r square minus a square cos square theta. So this 2aq, we already seen that that is the dipole moment. So we can write that as k p cos theta divided by r square minus a square cos square theta. From here itself, we can take the assumption that since a square, a is itself very, very small. So you know that the dipole, I showed you, it is very small, and the entire length of the dipole is 2a, and a itself is half of that. So it means that a square will be even smaller. So we can take the assumption that r being very, very larger than a, then we can say that a square cos square theta will approximately equal to 0. So we can take that assumption and this particular term will vanish. So we can take the assumption that r being very, very large than a, then this equation will transform to the form kp cos theta divided by r square. Okay. So kp cos theta divided by r square. Now, since these are vector quantities and we know that there is the angle cos in between them, we can write this as the dot product, because remember, if it is sine theta, it is cross, and if it is cos theta, it is dot. We can write this as k p dot r caps divided by r square. Why is the r cap there? As you all know, vector quantities need direction, and that is how we write them as vector quantities, and the dot product just indicates that the angle between these two quantities is cos theta. Now, why did we put a unit vector dot r caps there? It is to indicate that the angle between the dipole moment and the direction. That is, we considered the angle between r and the dipole moment. which is along the axis from minus q to plus q. So to indicate that, we are putting here a unit vector like this, so as to indicate that the angle is between the dipole moment and the unit vector or the direction vector, which indicates the direction. So in order to specify that, we are putting in kp dot r caps, and that is how we write kp cos theta by r square as vector term. So this will give you the potential due to a dipole. And now to specify a few cases, since there is an angle here, we have to specify special cases. Theta is equal to 0 degrees, theta is equal to 90 degrees, just 2 is enough. So we can say that if theta is equal to 0 degree, then cos theta will be equal to cos theta when theta is equal to 0 degree. Cos theta will be equal to 1 because cos 0 is nothing but 1. Then we can write it as kp divided by r square. So we will have maximum potential when the angle between the dipole moment and the direction vector is 0 degrees, which means that in the axial points we will have maximum potential. So we can say along anywhere here in this line we will have maximum potential, and that is indicated by kp divided by r square. And if the angle is 90 degrees, when theta is equal to 90 degrees, then cos theta or cos 90 will be equal to 0 because cos 90 is 0. Then we can say that anywhere along the equatorial plane the potential will be 0. Okay, so we have found out the two special cases. One is the axial line where the potential will be maximum, and there is the equatorial line where the potential can be 0. So those two are the special cases. Let us just revise what we actually just did. So in order to find out the potential of a dipole, what we actually did was we considered a dipole, and let this be negative and this be positive. So we considered a dipole which has equal magnitude and opposite polarity separated by a distance of 2a, and the dipole moment will be given by the equation vector p is equal to 2aq. So we considered a directional vector, that is r, from the center of the dipole starting from O to C, and we are going to find out what is the potential at the point C due to this particular dipole. That is, what is the potential due to positive charge and what is the potential due to negative charge. So in order to find that out, we have to find out what is the distance from positive charge to that particular point and what is the distance from negative charge to that particular point. In order to find that out, we name those two distances as R1 and R2. And using mathematical principles, we understood that this particular distance will be proportional to the distance, that is vector R. So we used mathematical principle. We drew a perpendicular from vector R to the point of origin of the dipole, and we knew that the angle made by the dipole and the directional vector, if it was theta, then we can take the assumption that cos theta, that is the side OM, will be equal to a cos theta. How did we find out that? The cos theta is equal to adjacent side by hypotenuse. Since the angle opposite to the 90-degree angle will be the hypotenuse, we know that hypotenuse is A and the adjacent side will be OM. And in order to find out OM, we used the Pythagorean theorem and we found out that it was A cos theta. And using this principle, we already knew that if we subtract that distance from the vector R, we will get the distance, that is R1. So we did that. R1 is equal to R minus A cos theta. And that is one side. Similarly, in order to find out what R2 is, we extrapolated the line, that is the vector R, backwards, and then we drew a normal from the dipole till the point it met the vector R. And then we considered a 90-degree angle here also, that is ANO. The side opposite to that particular angle will be the hypotenuse, that is also A, because the distance of the dipole is 2A. And then we can say that the adjacent side, which is NO, will be given by, or cos theta will be given by ON divided by A. So we can write that as A cos theta is equal to ON. And from that, just like that, we added this, that is NO plus R will be giving R2. So we can write it as R2 is equal to R plus A cos theta. So we now have the distance, that is R2 and R1, and we knew that in order to find out the potential, the formula is V is equal to KQ divided by R. And in this particular case, that is why we needed R1 and R2 in order to know the distance from those particular charges. We already knew what the charge was, and now we knew the distance. So in order to simplify that, the distances, that is R minus A cos theta and R plus A cos theta, then we simplified it into the form that is Kp cos theta divided by R square. We eliminated the A square cos square theta because R being very large compared to A, we assumed that it will be very small and close to 0. So we got this form, that is Kp cos theta divided by R square, and we can say that since this is cos theta, it will be a dot product, so we can write it as the dot product of two vectors, and the two vectors will be, the angle between two vectors will be denoted by the cos theta. In this particular case, those two vectors are P and R. So we can say that Kp dot R caps will be the representation of potential along a dipole using dot product. So we can say that Kp dot R caps divided by R square will be the potential. And since there is an angle between them, we can calculate the maximum, minimum and 0 point. So which just means that put 0 is equal to 0 degree and 0 is equal to 90 degree. We have two cases. When theta is equal to 0 degree, we can say that the angle will be parallel to the dipole, that is the distance vector or the vector R will be parallel to the dipole, that is along the axial plane, and along the axial plane the potential will be maximum given by the equation Kp divided by R square, and along the equatorial plane, that is when theta is equal to 90 degrees, the angle will be 90 degrees and the value of potential will be 0. And the only thing to remember here is that in the normal equation, V will be equal to KQ divided by R. But here for a dipole, it is different. When along with the distance, V would fall normally, that is, as distance increases from a particular point charge, the potential would fall by the ratio 1 by R, proportional to 1 by R. But here, for a particular dipole, the potential will fall in the ratio 1 by R square. So the potential will be falling more rapidly for a dipole as we move further and further away from that particular dipole. And that is all about potentials of a dipole. Now just to introduce a topic, that is equipotential surface. So what does equipotential surface actually means? It just means that the surface which has equal amount of potential. Let's say if you consider a point charge which is plus q or minus q or anything, and if I choose a distance r, a point p at r distance away from that particular charge, then if I considered a sphere, this is a two-dimensional board, so I can only show you a circle, but in actuality, imagine that it is a sphere. If you have a really round ball, imagine the very center of that ball. Then if it is at r distance away from the center, then we can say that every point along this circle will have equal potential. How do we know that? We know that because V is equal to KQ divided by R. So since R is not changing here, that is from here to here it will also be R, from here to here it will also be R. Since R is not changing, then V will not change, which means that for this particular charge, this surface or this along the surface, the potential will be equal, and that is known as equipotential surface. So we can consider another sphere which is r1 distance away. Then we can say that anywhere along this area or this particular line, the charges or the potential will be equal. The charge will have equal potential at anywhere along this line. Just like that, if we consider another r3, then again here it will have equal amount of potential anywhere along this particular path. So since R is not changing, then V will not also change. So we can say that equipotential surface actually means that a surface which will have equal potential everywhere. In the case of a sphere or in the case of a point charge, as we move radially outwards, it will be same at particular R distances away. So if the R is same, the potential of that particular point will be same. Now it is not just for a sphere, it can be a charged sheet or a charged line element. Just like in the applications of Gauss law, what if it is an infinitely long wire? Then what will be the case? In the case of an infinitely long charged sheet, we can say that the potential or the equipotential surface will be in the shape of a cylinder. That is, if we consider r distance away from that, we will draw a circle like this. Then anywhere along this particular circle with the radius r, the potential will be same because the radius is r. So this particular surface, let's say this is also r, then we can say that anywhere along this particular region, the potential will be same as long as the charges remain unchanged and the distance is not changed. And if you want to consider another equipotential surface, we can say that choose a bigger radius and then you will have a bigger cylinder which will be having equipotential surfaces along that. Don't worry about this. We'll be discussing in detail what equipotential surfaces are, what are its properties, and how we can introduce them. Okay. So we can say that for a point charge, the equipotential surface will be at the center of the sphere where the charges are at, and there are concentric spheres repeating one another. That is, one will be like this, one will be like this, one will be like this. Only the radius will be increasing. In terms of a charged line element, we can say that it will be concentric cylinders that are repeating in the increasing value of R. So this is all about equipotential surfaces for now. We will discuss in detail what is the basic properties of equipotential surface and the energy in the coming classes. So that is all for today. I hope you understood the class. I'll see you again very soon with more topics. Thank you.